All right. So our talk today will be given by Konstantinos Kavvadias from the University of Cambridge, who will tell us about the conformal removability of SLE4. Thanks, Konstantinos.
First of all, I would like to thank for inviting me and to give a talk in the seminar. I will talk about a joint recent work with Jason Miller and Lukas Schoug, both in the University of Cambridge. And this is based on a paper uploaded in the archive a couple of months ago. This is about the conformal removability of the trace of SLE4. So I guess all of you are experts in the field, so there's no point in giving definitions, the basic definition of SLE and properties of SLE. But I will start by giving a brief introduction on the notions of the conformal removability and the conformal welding. So, okay. So, I mean, as we all know, a subset of the complex plane is conformally removable if for every homomorphism defined on the complex plane, which is conformal on the complement of K, then for every such homomorphism is also conformal on K. Now, so let me talk briefly about the notion of conformal welding. So here we have a homomorphism phi mapping the unit circle onto the unit circle. So a conformal welding with respect to phi consists of a closed curve eta on the sphere and a pair of conformal maps, psi j's, mapping the unit disk onto each connected component of the complement of the curve in the sphere, such that phi is equal to psi to inverse composed with psi 1. So how are these notions connected to each other? I mean, if we know that the curve is conformally removable, then it is the only curve that can arise from the welding homomorphism phi. In a paper, I think announced 20 years ago approximately, Jones and Smirnov proved that if a set K is the boundary of a simply connected holder domain, then it is conformally removable. So here, by holder domain, I mean that if we take any conformal transformation, mapping the unit disk onto that domain, then it is holder continuous. Well, I mean, this implies that SLE kappa, when kappa is strictly less than 4, is conformally removable, since the complement of the curve in the upper half plane is a holder domain. This was shown, I think, by Rode and Schramm 17 years ago, approximately. So why someone should care in our case? Because as we mentioned, removability gives uniqueness of welding. We care about SLEs because it is known that they arise when gluing together LQG surfaces. Initially, it was done when kappa is strictly less than 4, but it has also been done when kappa is equal to 4, which corresponds to the critical case when gamma is equal to 2. In general, gamma is equal to square root of kappa. So this means that when kappa is strictly less than 4, we have uniqueness of the welding, but it was not known whether we have uniqueness when kappa is equal to 4, and our result also implies the uniqueness of the welding in the critical case. So, I mean, the notion of conformal removability of SLE4 is a problem which also has other applications, as we have seen, and also, I mean, it is interesting on its own. Because it's a very useful property in general of SLE. So how can we prove removability? As we mentioned, one condition that was proved in the work of John Smirnov, but more generally, if the corresponding uniformizing map has a weaker decay, it has a modulus of continuity which decays in a weaker sense, which has that kind of decay here, this exponential. Then we also have conformal removability for the boundary of the domain. But the problem is that the modulus of continuity of the corresponding SLE4 uniformizing map, by uniformizing map here, I mean that if we imagine the SLE4 drawn in the unit disk, starting from -I and targeted at I, then we consider the conformal transformation mapping the unit disk onto each of the components of the complement of the curve in the unit disk. then the modulus continuity of such a map decays much more slowly than the above Jones-Smirnov condition. This was shown in a joint work together with Jason and Lukas last year. In fact, in that paper, we also showed that the more general Jones-Smirnov condition that was stated and proved in the corresponding paper does not hold for SLE4 as well. So as we can see, this makes the problem of conformal removability hard because all the known conditions fail to hold for the SLE4 case. So here, first of all, before mentioning the conformal removability of SLE4, I will mention a deterministic conformal removability condition. Probably pedagogically is not the best way to do that, but I'm doing that in purpose because this deterministic condition can also be applied to prove conformal removability of other fractal sets, such as SLE kappa when kappa is larger than 4. So that's why I'm starting with that condition. And then I will show why SLE4 satisfies that condition almost surely. So here we start with a set X in the complex plane, and we fix a compact subset of X, and we take M to be very, very large, but fixed. So here we require that the upper Minkowski dimension of K is strictly less than 2. This makes sense because in order for a set to be conformally removable, a necessary condition is the Lebesgue measure to be equal to 0. Otherwise, if the Lebesgue measure is positive, then it cannot be conformally removable. And we take A here to be very small, such that this inequality holds. Right now this is not important. It is just for technical reasons. It will be clear in the next slides why we take A to be that small. And we consider a homeomorphism defined on the complex plane such that the complement of F, such that F is conformal on the complement of X. And here we want to impose certain conditions such that every such homeomorphism is also conformal everywhere. So here, for every positive integer n, we consider a family of conformal annuli, which is independent of the function f, such that for every a in that family, for every annulus a, its diameter is comparable to the minus n through some universal constants. And we also require that those families of conformal annuli are dense in the following sense: that for every point in our compact set and for all n sufficiently large, we can find k which is sufficiently close to n in this sense. It is at least 1 minus a squared times n and n. And an annulus a in this family, ak, which surrounds the ball centered at z with radius to the minus n. And we also have one more condition. We have this condition here, that we can find a path gamma in the conformal annulus, which disconnects the inner from the outer boundary of the annulus, such that the diameter of the image of the path gamma under the function f is at most this number here, which depends on k and on f, of course. Right now, it is not clear why we need that condition. It will be clear why we need that condition in the following slides. But that's the most important condition here. Equation inequality is 0.1. So here we have to. There are two things that we need to remember. First of all, that these annuli are dense in this sense here. That for every point in the compact set, we can fit an annulus, which can be made arbitrarily close to Z. And for every such annulus, we also have this path satisfying this inequality. So here, the goal is to show that that F is conformal under those conditions. So it suffices to show that F has the ACL property. This means that it is absolutely continuous on lines. So what I mean by that, I mean that if we fix any rectangle F in the complex plane and we sample T according to the Lebesgue measure, on the interval between C and D, then and we consider for such T the line with the imaginary part equal to T. This line cuts the rectangle F horizontally. Then we want to show that for Lebesgue almost every T in that interval, the restriction of F to the part of the line in the rectangle is absolutely continuous. And the same, of course, is true when instead we cut the rectangle with lines vertically. So what is the idea then? The idea is to consider the part of that typical line in the rectangle and to divide it into intervals of length to the minus n here, when n is arbitrarily large. Then we consider the subfamily of those intervals such that the set X intersects. And for every such interval, we fix a point of intersection and we consider the corresponding annuli A and the paths gamma. So the point is here, in order to prove that F has the ACL property, since it is conformal outside of the set X, the point is to bound the variation of the F near the points of intersection of X with a line. And near those points, we introduce this annuli gamma, this annuli A and the paths gamma. So condition here, inequality 0.1 helps us to bound the variation of F near those points of intersection. So here the number of those intervals is of this order here, is 2 to the 1 minus 5 times A times N. This is because we take A to be sufficiently small, but fixed. And also the integral by Fubini theorem of the derivative of F, of the square of the derivative of F near a very small neighborhood of the part of the typical line in the rectangle is at most a constant times 2 to the minus 1 minus A squared times N. This comes from Fubini theorem. So combining these two facts together with the inequality that we mentioned earlier, we obtain that the variation of F near the points of intersection of X with that typical line is of order 2 to the minus, is at least a constant time 2 to the minus A times N over 2. So I guess for me, it's the right time now to draw some pictures and explain a bit better what's going on. So if you don't see what I draw, please let me know. So here we imagine that we have the part of the typical line intersecting the rectangle. And we also consider our set X. I have drawn that in purpose so that it looks like an SLE4. And we consider the corresponding intervals here that this set intersects. So let's call these intervals the IJs, is the interval I2, I1, I2, up until IMN. And remember that for a typical line, Mn is at least a constant times 2 to the 1 minus 5 times A times N. And for every such interval, we consider the corresponding annuli surrounding those intervals. And we also have the corresponding blue paths disconnecting the inner from the outer boundary of the annulus. So the point here is the following. I mean, for simple topological reasons, we have that the diameter of the intervals ij's, of the image of the intervals ij's under the function f, is at most the diameter of the image of the path gamma j's under f. And this is at most a constant times 2 to the minus 1 minus a square times 1 minus 3 times a times n. This is because of 0.1 inequality, plus 2 to the 1 minus a times n times the integral of f. Here I have aj, the corresponding annulus of the derivative of f. So here I sum over j. So if I sum over j, which is exactly this sum that we need to bound in order to deduce that f is absolutely continuous, then this would be at most a constant. Here in the first term, I multiply this first term by mn, by the number of those intervals, but mn has this bound here. So if I take a sufficiently small, as I have done in the beginning, is at most a constant times 2 to the minus 1 a times n divided by 2. Here I still have this term here, this term remains, and I have the sum of those integrals. So remember, every such annulus is contained in the neighborhood of the part of the line on the rectangle of size of radius 2 to the minus 1 minus a squared times n. So this is 2 to the 1 minus a times n. And here I have the integral of the square of the derivative of f of that neighborhood, on that very, very small neighborhood. But the point is that by Fubini theorem, this term behaves just like 2 to the minus 1 minus a squared times n. This comes from Fubini theorem, and because the derivative of f is defined almost Lebesgue almost everywhere, because the Lebesgue measure of the set is equal to 0. So this overall, if we take a sufficiently small, is at most a constant times 2 to the minus a times n over 2. So in this way, we have managed to bound the diameter of f near those points here of intersection, using the inequality that I mentioned earlier on the diameter of the image of the corresponding paths under f. I mean, away from those points, we are in a good shape because the function is conformal. Therefore, again, I can bound the variation away from those points by just, again, applying a Fubini theorem. So the whole point is to bound the variation near those points of intersection. And that's why, now I should change. And that's why exactly what this inequality here on the diameter on the image of f, or the image of gamma under f does. So here, then under those conditions, as we have seen, at least heuristically, the function f is absolutely continuous for a typical line. But here, the point is to introduce further conditions which guarantee the existence of such a path gamma. That is the whole point here, and that's the real hard work. Because we need to introduce some further conditions. So here, I have here some conditions. I will explain every one of them. So here, for every such annulus, A, conformal annulus, we require that we can find simply connected subsets of the complement of X in that annulus, the subsets UJs. Here, these subsets, we do not require them necessarily to be simply connected components. They are just simply connected subsets. And we also require segments, IJs, which are contained on the pairwise intersection of their boundaries. I mean, we require that the boundaries of those domains pairwise intersect. And we also require that there exists a measure μj on each segment ij, such that the following conditions hold. The first condition has to do with a lower bound on the mass of every such segment under the measure μj, is at most a small number but fixed, times to the minus dj times k. I mean, this condition makes sense because I mean that does not come from nowhere. Because in the case of SLE4, we will show that these conditions are satisfied when mu j here is the restriction of the natural parameterization of SLE4 on the segment ij. So here one holds for SLE4 when the I here is equal to 3/2, which is the household dimension of SLE4. And we also require an upper bound on the measure mu j. So we need this upper bound here related to the diameter of every subset of every Borel subset of uj. And again, this makes sense as well, because again, this is true for the natural parameterization when the I again is equal to 3/2. And condition 4 here, I skip for the moment condition 3 because this is the most difficult one. So condition 4 isn't bound. Here we consider a Whitney square decomposition here Wi of every such set chosen in some measurable way. I remind that the Whitney decomposition is a family of squares with length to the minus n for n an integer, such that they are pairwise disjoint and their distance to the boundary is comparable to their diameter, to their size. So condition 4, here we require that the number of squares, Whitney squares with length of side length to the minus j, such that a hyperbolic geodesic starting from an interior point zj and adding at some point uj intersects for some points of uj is at most a constant times 2 to the di plus a times I minus k. This bound here again makes sense in the case of SLE4. Because remember when the I is equal to 3/2, because we can estimate the probability that the SLE4 hits a fixed ball of size epsilon, for instance. And so it's exactly the same here, because a Whitney square of length to the minus j is a so I mean the condition 4 makes sense as well. So what is not obvious, very easy to see, is condition 3. So again, we start with the Whitney square decomposition of the set ui. We fixed an interior point, and we require that for a large fraction of points w in the segment ij with respect to mu j, we have the following. If we consider the hyperbolic geodesic starting from the interior point and targeted at this point w and terminating at w, then for every Whitney square that such a hyperbolic geodesic intersects, we have this upper bound here on the hyperbolic distance between the interior point and the square is at most a constant times 2 to the k. 2 to the k here, 2 to the minus k is the size of the annulus. So here, this constant here comes from scaling, times the length of q and all to the power of minus a. So I will explain in a few minutes how this condition helps. This condition here helps to find an upper bound on the image of those paths that we construct. So let me mention, okay, so here how can someone construct those paths? Remember, condition 3 here holds for a large fraction of points with respect to the measure mu j on every intersection of the boundaries. So we can pick such a point such that condition 3 holds for both of the domains ui minus 1 and ui, whose boundaries intersect. And then for every such point, we consider the corresponding hyperbolic geodesics connecting the fixed interior point with the boundary point, and then we concatenate them. We concatenate these hyperbolic geodesics in order to obtain the path gamma. So here condition 3 helps us to bound the diameter of these geodesics, as we can see here, under the function f. And therefore, we obtain the required bound for the path gamma by just taking a union bound, by summing the diameters of all these hyperbolic geodesics here. Of course, here we use condition 1, 2, and 4, because these guarantee that condition 3 holds for a large fraction of points uj. I mean, these two combine together in order to obtain this, but the condition 3 here is the core of the argument. So let me draw some pictures then to explain a bit better. So here we have the following. So here we have our annulus, and we have our set. So again, I will draw that in purpose so that it looks like an SLE4. So the SLE4 does something like that. And then we fix segments, the green segments, which are part of each crossing of the SLE4. Then we fix points, WJs, on every such crossing. And again, we also fix some interior points. And then we consider the corresponding hyperbolic geodesics, these blue paths, connecting the interior points with the boundary points. And then we concatenate them. So the concatenation of all these blue hyperbolic geodesics will be the path that we need. And condition 3 that I mentioned earlier allows us to bound the diameter of the image of those hyperbolic geodesics under the function f. And then we just use a Euler bound. So that's roughly speaking how condition 3 works in our case. Okay, so this is a general picture of what might happen. So here we have this conformal annulus. This is the blue region, and we have the corresponding components. These are the green components. Of course, in the case of SLE4, this is not the right picture, of course, because it is a simple curve. So this is a general picture. So here, in other words, the point here is to introduce some conditions on the intersection of their boundaries on these points, such that these conditions guarantee the existence of all this of the path disconnecting the inner from the outer boundary of the conformal annulus, satisfying this bound that we mentioned earlier. Which leads, of course, to the fact that the function f is absolutely continuous for a typical line restricted to every rectangle. Therefore, it has the ACL property. So here, as I mentioned, one quick comment about the more general condition that I introduced is that it does not require that the set is the boundary of a simply connected domain. That's very important. Instead of, because the Jones-Smirnov conditions that I mentioned earlier, this require that the set is the boundary of a simply connected domain. So in that case, our deterministic condition does not does not have that requirement. Therefore, it can be applied to other sets as well, apart from the SLE4. So here, the goal is to prove that SLE4 satisfies this condition almost surely for every compact set, where the μj's are the natural parameterization restricted to the corresponding intervals, to the corresponding segments, ij's. And here the di's are equal to the Hausdorff dimension of SLE4, which is equal to 3/2. So here the strategy is to consider Euclidean annuli, simply Euclidean annuli here. But of course, in the paper, we do not exactly consider Euclidean annuli. We consider conformal annuli, which approximately look like Euclidean annuli in order to avoid some technicalities. But everything works the same for Euclidean annuli as well. So we can just imagine that in the case of SLE4, we consider Euclidean annuli. So as I mentioned earlier, 1 and 2 come from properties of natural parameterization, and they're not very hard to see. Condition 4 comes again from the following observation, that if we're in the upper half plane and we fix a large ball, but fixed, and we take a very fine grid of points on that ball, And we count for L large, we count the number of points such that the SLE4 intersects a ball of radius of order 2 to the minus L centered at those points. Then the expectation of those points will be at most a constant times 2 to the 3 times L over 2. So this means that the number of those points is at most 2 to the 3 over 2 plus A times L for all L sufficiently large almost surely. And this where, I mean, where condition 4 comes from. It's basically this property of SLE4. So here, what is the setup? Again, the setup is the following. We just fix a Euclidean annulus. And we consider eta j to be the crossing that eta makes of that for that annulus. I mean, of course, we assume that we are working on the event that SLE4 hits the inner boundary of this fixed annulus. And here with eta 0, I call the right side of the first crossing of the curve of the annulus, seen as prime edge, of course, and eta n plus 1, the left side. And the rest of the crossings are, I call them eta j's. So here we treat the first crossing first. This is locally described by a two-sided whole plane SLE4 from infinity to infinity, which passes through 0. So here the point is that condition 3 that I mentioned, which is the most important condition, is true for that curve eta tilde, the two-sided curve, with high probability if we have M large and fixed. So by conformally mapping back onto the upper half plane, the same is true for the left and right sides of the first crossing of the curve in the complement of the first crossing in the annulus. So here, this argument proves that condition 3 holds for the first crossing, but in a larger domain, because we want to make sure that condition 3 holds for the connected component of the complement of the entire curve in the annulus, whose boundary contains the left and right sides respectively of the first crossing. But the point is that condition 3 that I described earlier is local. Is local in the sense that if we replace this component U of the complement of the first crossing by the components of the complement of the entire curve in the annulus, whose boundary contains the right and the left side of the first crossing, then condition 3 still holds, possibly by taking the segment to be smaller. And this comes just by comparing the corresponding hyperbolic geodesics. I mean, the hyperbolic geodesics near those points, near those boundary points, if I change the domains, they're approximately the same. They do not change much their hyperbolic distance. And this of course is enough to show that the condition 3 also holds if we would take the domain to be a bit smaller, as we do in that case. So here, this is a way to sample the two-sided curve. So let me draw some pictures again to make some things a bit clear. So here, how does this curve might look like? So here, this is we start with a curve from infinity to 0, which is a whole plane SLE4 2. And conditional on that, on the complement, we draw an SLE4. And here we show that condition 3 holds if for instance, we take the two-sided curve in a fixed rectangle, in a fixed large rectangle, then the condition 3 holds for some segment here, for the part of the curve inside this rectangle. Then we conformally map that picture in the upper half plane. So here we have our annulus, and we have the corresponding curve here. So here the point is that this crossing here, the first crossing of the image of that picture here on the left side, will be absolutely continuous with respect to the corresponding first crossing of an SLE4. Therefore, condition 3, because this condition is a local condition, as we described earlier, calls for a segment of the first crossing. But if, however, restrict ourselves if we are in a bit larger domain, in the complement, in the connected component of the complement of the first crossing in the annulus. But the point is, as I described earlier, because this condition is local, it is still true if I draw the rest of the curve. So in that case, it will still be true for these two domains here, possibly by taking this segment to be a bit smaller or much smaller, but it's fine for our purpose. So this way, this is roughly how we treat the first crossing. How we prove that condition 3 it can hold with arbitrarily high probability if we take m very large, and of course provided that we are working on the event that the SLE4 hits the inner boundary of the annulus. So here, the next step then is to consider the rest of the crossings and prove that the condition 3 also holds for the rest of the crossings and for the rest connected components. So what is the idea here? The idea is to couple the curve, the SLE4, with the GFF H on the upper half plane, such that the SLE4 is the level line of H. So here, this is the setup. So we consider tau zk to be the first time that it hits the inner boundary of the rectangle. And we consider the connected component of the complement of the first crossing, whose boundary contains the inner boundary of the rectangle. And then we take this picture and we map it onto a rectangle of size 1 by hzk. Here, hzk is a positive real number, but random. And we conformally map it such that the right side of the first crossing is mapped on the left side of the rectangle, and the left side of the first crossing is mapped onto the right side of the rectangle. There's a unique transformation satisfying these properties. And we consider the images of the crossings of the annulus made by SLE4 under that conformal transformation. And we consider the part of those crossings here, eta j tilde, which are a bit away, as we can see here in this, a bit away from the upper and lower boundary of the rectangle. It will be clear why we choose them in this way. So this is the picture here. Here, I guess we can forget this blue annulus here because this is the way we choose it, the conformal annulus. We just consider a very good shape here, a very good annulus, and then we take the inverse image under this conformal transformation psi zk here, which sends z to 0 and the tip of the curve, let's say, to minus I, just to avoid some technicalities. But we can imagine that this is just a Euclidean annulus here, and forget about this picture. So this red part here is the first crossing of the annulus. And then we consider this picture here minus the red part, and we conformally map it onto that rectangle here. This is the image of the right side. This is the image of the left side of the first crossing. And we consider the crossings inside this rectangle, and we prove that the corresponding properties hold for that rectangle here. And then we conformally map back onto the conformal annulus to prove that these properties hold for that annulus as well. So this is the goal that I have just described, conditionally, of course, that we hit the inner boundary of the annulus. But here we have an issue because if we consider the initial GFF and we consider it on the rectangle by conformal transformation, then this might have complicated boundary values on the upper and lower boundary of the rectangle here. We know the boundary values on the right and left sides will be pi over 2 and minus pi over 2 respectively. This comes from the level line coupling. But we don't have control over the boundary values on the upper and lower boundary. So the point is, the key idea here is to replace that field by a simpler field on the rectangle, this field h hat that I call it, with boundary values pi over 2 and minus pi over 2 on the left and right side, and 0 on the rest of the boundary. And then we consider the corresponding crossings of this coming from this field. But for that, we need somehow to obtain these crossings in a measurable way with respect to the field. Therefore, the main step here is to introduce an exploration procedure, which discovers these crossings eta j tilde as a measurable function of the corresponding field. That's the whole point. I guess I will have some time to mention how we actually construct this exploration procedure. And of course, do the same for the field h hat to obtain the corresponding crossings eta j hat. Then we show that with high probability, the desired conditions hold for the crossings eta j hat in the rectangle. Then by comparing these two fields, the original field and the field h hat, we show that we obtain that this also holds with high probability for the crossings eta j tilde of the original field. And then we map back onto the original annulus to obtain that these properties also hold for the crossings of the curve there. So here, as we can see, since we need to compare the fields, we need somehow to compare the random Nikodym derivatives of the corresponding restrictions of the field on this rectangle here. So therefore, we need to consider, instead of deterministic scales here, k, we need to consider random scales at which the situation is good. So what I mean by that here, this is an illustration of how things might work. So here we perform the exploration that I mentioned, which somehow discovers the crossings in two rectangles, in an upper rectangle and in a lower rectangle here. So here we have a bunch of crossings. We discover other crossings as well, apart from the crossings that we need. So here, these blue crossings here in the upper and lower rectangles will be part of the original crossings eta j tildes. And here will actually be the continuations of the crossings when restricted in the mid rectangle here. So the point is that here the explorations on the upper and lower rectangles discover all these crossings in a measurable way. So conditional on those crossings, the remaining parts of these blue crossings, which are the crossings eta j tilde, will just be the level lines of the restriction of GFF here in the middle rectangle, starting and ending from the ending and starting point of a blue crossing discovered either in the upper rectangle or in the lower rectangle. Of course, here we also have these excursions here as well, but I mean these are not the crossings that we need, but we are fine because the crossings that we need have already been obtained in a measurable way, just like we wanted. But the point is that we will discover other crossings as well, these orange crossings here, and also these excursions from the boundaries of the upper and lower rectangle. So again, this is another picture. So here we perform the exploration on the rectangle, and then we map back here in the conformal annulus. So we have these smaller annuli here with the crossings discovered, and the original crossings of the curve will lie between these two annuli here, containing these crossings. So here, as I mentioned earlier, we need to control the random Nikodym derivative of these laws here, of the law of the original field with respect to the new field. So remember here, the key observation is that these two fields have the same boundary values on the left and right sides of the rectangle. But their boundary values on the upper and lower boundaries might differ, of course. That's why I consider the crossings to be a little bit away from the upper and lower boundary. So to do this, as I mentioned earlier, we consider different random scales, these kj's here, depending on z. So this is a random non-decreasing sequence of positive integers, instead of considering deterministic scales of the annulus. So roughly speaking, these scales are the ones at which the boundary values of h, or of this field, if we map on the rectangle, are bounded from below and above by universal constants. So if we know that, then of course we can compare the fields. That's why we consider this sequence of random scales. These are the good scales at which we can compare the fields. So here, and then if we do that, I mean, their definition is a bit more complicated, of course, because there are other factors that we need to consider. But the main idea is that these are the ones at which the boundary values are comparable. So here, these kj's are dense in the following sense, that almost surely, if we fix any compact set, then for all n sufficiently large, if we take a very fine grid of points of k, then we can find a scale here, which is at least 1 minus a squared times n and n. This also comes from the condition that we posed in the deterministic case. So this, I guess, comes from a Borel-Cantelli type argument. And remember that for every such scale, we have that the desired properties hold with arbitrarily high probability by taking m very large. Then again, we must have that at least one of those scales, we can find at least one of those scales, we will find an annulus, provided, of course, that the curve gets really close to z. We always work on that event to make everything sense. Then we can find such a scale, such a random scale, such that the desired properties hold for the corresponding annulus. So here we apply some kind of Borel-Cantelli type argument twice here. So first we show that the scales are dense, and since for every such scale the desired properties hold with very high probability, with arbitrarily close to 1, then this will also be true for at least one scale. And since these random scales are extremely close to n, then we obtain our desired properties. So here, then the next step, I guess, for me to mention is the exploration. How can someone obtain these crossings in a measurable way, and what kind of exploration that we're considering? Okay, so here we just fix a rectangle here with size 1 by h. H is a fixed number, positive. And we consider a rectangle whose upper and lower boundaries are bounded away from the upper and lower boundaries of the original rectangle. And this is the rectangle at which we are going to consider the exploration, which discovers plenty of crossings. And as I mentioned earlier, we start with a GFF on the rectangle with boundary values given by lambda. Well, here by lambda, I mean pi over 2. This is the general notation. The lambda in general is equal to pi over square root of kappa. Well, in our case, kappa is equal to 4. Therefore, we can imagine that this lambda is pi over 2. And 0 elsewhere in the rest of the boundary. So here, let me describe it in pictures better. So this is the picture. First, we start with a picture on the left-hand side. So here we fix u to be very, very small, but fixed, it's fixed. And we consider the midpoint of the left side of our rectangle. And we start this blue curve here, this curve eta1. So this curve will be the level line of height u of the field h. So by that, I mean this is the 0 level line of the field h minus u, this blue level line. So this is an SLE4 raw type process. And we stop it up until the first time that it either hits the upper boundary, the lower boundary, or the right boundary. So here for the first stage of the exploration, here I will describe the first stage, and then I will explain how we can iterate this procedure. Okay, so here because of the corresponding values of the corresponding weights of the force points, this blue curve will not hit the right side of the rectangle. So this means that it either hits the upper boundary or the lower boundary of the rectangle. Of course, it will hit multiple times the left side of the boundary of the rectangle. So suppose that we are in the first setup, the first case that this blue curve hits the lower boundary before it hits the upper boundary. So in that case, what we do is that we consider the uppermost point of intersection of the blue curve with the left side of the rectangle, and we draw this red curve. So what is this? This red curve is the level line of minus h plus u. So in other words, is the time reversal of the level line of height u of the field. And again, we stop it up until either it hits the upper boundary of the rectangle or the lower boundary. For the same reason, it doesn't hit the right side of the rectangle. And also it doesn't hit the left side of the blue level line, apart of course from its starting point. Again, this is due to the interaction rule of SLE kappa rho processes in general. This has to do with the value of the force points. In that case, the corresponding value of the force point will be larger than 0, which is equal to kappa over 2 minus 2. So when kappa is equal to 4, this is 0. And for that range, the SLE4 cannot, the SLE type curve cannot hit the corresponding segment. So here it either hits the upper boundary or the lower boundary. So suppose that it hits the upper boundary first. Again, it will hit multiple times the left side of the rectangle. So in that case, we consider the first crossing, discovered in the first stage of the exploration, to be the concatenation of the right side of the red level line with the left side of the blue level line. So this concatenation here will be the first crossing, and the boundary values of the field will be equal to minus lambda plus u on the right side of the first crossing. That's the first scenario, but we might also have a second scenario here, that this red level line might hit the lower boundary of the rectangle before hitting the upper boundary. So in that case, we draw another level line. We consider the uppermost point of intersection of the left side of the red level line, and we start this blue level line, which is the level line of h minus u. So in other words, the level line of height u of h. And again, we stop it up until the first time that it hits either the upper or the lower boundary of the rectangle. For the same reason, it doesn't hit the right side, and also it doesn't hit the left side of the red level line, again due to the interaction rules. So here, if this blue level line x hits the upper rectangle first, then we are done. This is we have completed the first stage of the exploration. And we consider the first crossing to be the concatenation of the right side of the blue level line with the left side of the red level line. This is the first crossing. Here, of course, the boundary values of the field will be equal to lambda plus u. And again, we repeat the same procedure. If this level line, the blue level line, hits the lower boundary before the upper boundary, then we iterate this procedure again and again up until we reach a situation which looks like either this one here or that one. So eventually we will obtain such a situation. It's not obvious at all, of course. If I have some time, I will explain why this is true. So in any case, we discover a crossing, which will be a concatenation of a blue level line with a red level line. And the values of the field on the right side of that crossing will either be minus lambda plus u or lambda plus u. This is why we call this crossing a crossing of height u. So here, coming back on the left side, here on the first case, if this blue level line here, the origin hits the upper boundary of the rectangle before the lower boundary of the rectangle, then the roles of the red and blue level lines are reversed. So in that case, the red level line will play the role of the blue level line, and so on. And then we repeat exactly the same procedure that we described here. So this completes the first stage of the exploration. And okay, so this is everything that I have said in words. So here, how we can iterate this procedure. So the point is to iterate this procedure and discover more and more crossings. So suppose that we have defined the exploration after j steps without discovering a level line which hits the right side of the rectangle. We call this crossing, let's say, Lj here. This is the jth crossing discovered with height u. So this means that the boundary values of the field on the right side of the crossing are either lambda plus uj or minus lambda plus uj. So here uj might be negative as well, or 0. Of course, it's not necessarily positive if we iterate the expression many times. So here, the point is to repeat, to iterate the previous procedure, the j equals 1 case. So for that, we will need a height here. So if the boundary values of h are equal to lambda plus uj in the crossing, then we consider the uj plus 1 to be equal to uj plus u. U is the fixed positive number. And then we consider the corresponding level lines of height uj plus 1 for this value of uj plus 1. We repeat exactly the same procedure where u is replaced by uj plus 1. If h now has boundary values minus lambda plus uj on the crossing, then we consider uj plus 1 to be uj minus u. And again, repeat exactly the same procedure with u replaced with that value of uj plus 1. But here there's a small difference. The difference is that if uj plus 1 is not is on that regime here, is between minus 2 times lambda and 0, then some of the level lines might hit the right side of the rectangle before exiting either the upper or the lower boundary. So in that case, we stop the exploration. And that's it. I mean, we do not proceed any further. But if uj plus 1 does not lie on that interval, then none of the level lines drawn will hit the right side of the rectangle, and then we proceed as before. We iterate the previous procedure. I mean, the whole point is the main description is the j equals 1 case. So here, in this way, we have obtained multiple crossings Lj of the rectangle, such that they pairwise intersect. And the point is why someone should define the exploration in this way. I mean, we define in this way because the crossings with height equal to 0, where uj is equal to 0, are exactly the crossings uj hat. Here, they are part of those crossings. Why this is true? Because if we go back to, where is it now? Yes, to that picture. So here we have performed the exploration on the upper and lower rectangles. So here the blue crossings here, someone should imagine them to be the 0 height crossings that we described earlier, and the orange crosses are the crossings whose height is not equal to 0. So remember the crossings here in the middle rectangle, which make it from bottom to top. These are level lines of height 0. So this means that they cannot intersect the orange crossings due to level line interaction rules, because their heights are not equal to 0. Therefore, since these crossings have to cross necessarily the upper rectangle here, they have to do it by intersecting one of the 0 height crossings. But again, due to level line interaction rules, when two level lines with the same height intersect, then they merge. So this means that the 0 height crossings that we have discovered are actually parts of the original crossings of the rectangle. So that was the point of introducing this procedure in this way, with all this height of crossings and so on. I mean, the point is to obtain these crossings in this measurable way. And of course, almost surely this exploration discovers finitely many crossings. This means that eventually we will discover a level line which hits the right side of the rectangle before either the upper or the lower boundary. And this is the last thing that I would like to mention. I guess I have a couple of minutes. Okay, so how to prove then that the number of crossings is finite? Then the first part is to show that it is very unlikely that we discover a crossing, a level line, a crossing actually with height very, very large. So in other words, the probability that we discover a crossing of magnitude at least m is at most a constant times this exponential as m tends to infinity. Of course, I do not think that this is the optimal behavior, but it's more than enough that we need, because here we have a very strong decay. And what's the point? This is the main part of the argument to prove that the exploration discovers finitely many crossings. So how can someone see this? This is not very difficult, because imagine that we consider the rectangle, and we consider the line which cuts the rectangle horizontally in the middle. And we consider, and in that line, with imaginary part I times a plus b over 2, we consider points with spacing equal to 1 over capital M, which these points are very, very dense, where capital M is large. And then we consider the conditional expectation of the field evaluated at those points. until each point gets disconnected by a crossing from the right side of the rectangle. So here, what I mean by conditional expectation, remember that I have drawn level lines so far. So this is a local set. Therefore, I can decompose H on the component of the complement of the level lines containing this point here, let's say Vm, into a zero boundary GFF and a harmonic function. So here I just consider this harmonic function evaluated at each point and stop it, of course, up until the first time that it gets disconnected from the right side, and parameterize it, the entire local set, the entire procedure, by low conformal radius as seen from each point. Then this will evolve as a Brownian motion. The harmonic function evaluated at this point. So, of course, this changes with time because we discover more and more level lines. So the main idea is that whenever we discover a crossing with very large height, then the corresponding Brownian motion will change value by a large amount. By amount, at least, I think a constant times m square. In a small amount of time, in an amount of time of order log m, log capital M, because remember we have parameterized everything by log conformal radius as seen from each point, and the spacing between those points is equal to 1 over capital M. And then everything reduced to that estimate here. So here we have to replace here M by square root of M in order to be consistent with this quantity here. But the point is that this is known, this is a known fact for Brownian motion. It behaves like that. So that's where this decay comes from here. So this means that it's very unlikely that we discover a crossing with very large height. So conditional on that event, if we consider the point V capital M minus 1, which is the point which is closest to the red side of the rectangle, then this point is very likely to be disconnected from the right side by a crossing which actually hits the right side of the rectangle. And this makes sense because if we consider a crossing which gets arbitrarily close to this point here, then it will also be very extremely close to the right side of the rectangle as capital M tends to infinity. Therefore, it is very, very likely that this crossing actually hits the right side of the rectangle, this level line actually, and therefore the exploration terminates by discovering a crossing which actually disconnects this last point here, which is very close to the right side of the rectangle, from the right side of the rectangle. So that's the main idea, and that's exactly. Let me finish with this remark. That it's exactly the same argument here that shows that eventually the first stage of exploration is completed. Again, we divide the middle line here by points with very, very small spacing. And then we consider the corresponding harmonic function evaluated at those points. Then again, this procedure, if we discover too many level lines here, then this amounts to the Brownian motion changing values by a large amount in a relatively small time. Therefore, eventually, we will obtain either that picture here or that picture here. That means that the first stage of exploration is well defined. And using, of course, that argument, again, we prove that the exploration terminates almost surely. Therefore, it is well defined, and we obtain all of the crossings that we need. Of course, we obtain a lot more crossings, but that's fine. I mean, the point is to obtain the crossings that we actually need, the crossings of the original curve, and then use the previous procedure to compare the fields, do the same for the original field, and then conformally map back onto the annulus and prove that with arbitrarily high probability these properties, the 4 properties I described earlier, hold in our case. Conditionally, of course, that we hit the inner boundary of the annulus, of course, on that event. So I guess, do I have to say anything more? No. Yeah, I guess that's. And of course, a final remark is that this deterministic theorem that I described earlier can be applied, as I mentioned, to proving that the SLE kappa, when kappa is larger than 4, is conformally removable. Because this has the advantage that it does not require the set to be the boundary of a simply connected domain. So it's general. It's a very general deterministic fact. That's why I chose to present the deterministic theorem first, and then mention all the things related to SLE4 and how we apply this theorem in the case of SLE4. So I guess thank you. Then I don't have anything else to mention. So.